Hi, this is Jason McIntosh with McIntosh Applied Engineering. This video is going to cover some of the basics of the frequency response measurement module, which is a part of the Aries acoustic design system. To start the module, you're going to go to the New Modules menu and find the frequency response measurement module and select it. So this now created a new instance of a frequency response measurement module. The purpose of this module is to use PC sound cards to do fairly simple acoustic measurements in an inexpensive way. So I'm going to pull the manual over here. You have a PC, you have a playback device that generates an output, you have a linear system, and then you measure two outputs from that linear system with a recording sound card. And the frequency response measurement module will measure the transfer function between those two signals, or it'll show you the magnitude of an individual, the spectrum magnitude of those individual channels as well. So that's the main idea of this, and we'll jump into it. The interface has a number of tabs here. This is very similar to the modules that measure acoustic impedance. There's an acquisition tab where you're going to spend most of your time acquiring the data. There's a setup tab that you'll typically just go to once to set up your system. A plotting tab, where you'll look at all your results. And then finally, a clipboard and file tab where you'll do some import exporting of the data. If I go to setup, you can select your sample rate. You can select what sound card you want to use as the recording device. And then you can select what sound card you want to use as the playback device. I usually use this M Audio device. You can select whether or not an input channel is going to be a voltage measurement, a microphone measurement, which would measure pascals. You can have a digital level, or you can just simply turn that channel off completely. If you have a B&K Nexus amplifier, it will read the microphone sensitivity directly from the Nexus, or you can enter a manual microphone calibration level by itself. Playback can be out of the left and right channels together, or just out of left and right, or you can have the left and right signals opposite polarity to double your drive level if you'd like. There are a couple buttons here to test your system. This button will play a quick 3-level tone out of the sound card output and then record the signal levels in. I'll press this. We heard a quick little chirp there. The output signal is shown in blue and the recorded input signal is shown in green. As you can tell, we do have some input levels. It is slightly delayed from the output. It's mostly due to sound card latency. If you notice, the right channel has some odd behavior at the beginning and ending. This is because the way I currently have my system set up is shown here. I'm using a May speaker driver with a bare electric microphone directly above the output. Then I've got another microphone on a 12 centimeter long tube. And so that unusual behavior at the beginning and ending of that chirp is that tube getting excited with some transient signals there. Also, the only external hardware that I'm really using here is a microphone amplifier offered from May. It's the May 206. It's got inputs that will provide phantom supply for your microphones if you want them to or not. It's also got some inputs that allow you to provide a separate power supply line for your microphones. The amplifier inside is computer controlled and it has digitally selectable gains from minus 20 dB padding to a plus 40 dB signal gain, as well as a calibration signal level. I'll show you that in a minute. Then the outputs come out here, and these are going to my sound card. So this is what the current system looks like that we measured this chirp with. This button plays a constant full-scale output to your speaker. Typically what you'll do is you'll turn your amplifier way down, start this playback, gradually turn your amplifier up so that you make sure that everything's at a good signal level and you're not burning your drivers out with an overload from your amplifier, and then you'll click this again to terminate the playback. And then if you have a Nexus, you can select the COM port that it's on here. So once you've set up your system, you go to Acquisition. Acquisition consists of a calibration stage and then 3 actual measurement stages. The calibration consists of calibrating your input levels to identify the maximum peak to base input levels in voltage. To accomplish this, Aries has this button which will, if you press it, it'll ask you to put a calibration signal on the left and right input channels. The calibration signal is supposed to be 100 millivolts peak to base at 1 kilohertz. Now, May sells a device which generates a signal level, or that May 206 amplifier, which I showed you. This amplifier can be told to set up to produce a calibrated output for it. Now, the control program for that amplifier is shown here. Right now I've got the phantom turned on, the left and right channel, and 20 dBs of gain. To do a calibration, I'm going to select the calibration signal for the left channel, 0 dB gain for the left channel, calibration for the right channel, 0 dB gain for the right channel. So now there is a signal, there's a calibration level present on both the left and right channels. I'll go back here and tell it, okay, the signal level is present. And it calibrated, and again, it found about 5.6, 5.7 volts maximum input level for this sound card. This is the signal that it recorded. You can zoom in by scrolling the mouse wheel, and the signal on the left and right channels are pretty much identical, and the calibration is nice and not clipped. It's not distorted, so we got a good calibration from this. Since we selected manual microphone calibrations, these fields enter here. The microphones that I'm using have a nominal sensitivity of minus 46 dB volts at 1 Pascal. However, I usually set up the amplifier to have a gain of 20 dB, so I will do that here. Turn phantom supply back on, cal signal off. So since I've got a 20 dB gain here, the minus 46 becomes minus 26 dB volts at 1 Pascal sensitivity. You can use this button here, which will measure the RMS level on the inputs if you want to manually calibrate a microphone with an external microphone calibration device. By hitting this, it'll measure the RMS level on the left and right input channels. Now, because I turned my cal signals off, this is just recording my voice. So it's reporting the RMS level on the left and right channels here due to my voice. But had you connected a calibrator up, you could use these levels to figure out what the sensitivity of your microphones are. The output from your sound card can also be calibrated. I happen to know that with my current amplifier settings, the maximum output is 10.5 volts, but you can also calibrate the output with these buttons. These are described in the manual, including a loopback feature where you can calibrate the output by connecting it to a calibrated input. So that's the calibration section. The measurement sections, I'll start, there's 3 main measurement types. There's a step sine, which plays a series of constant tones out. There's a chirp, which will play a frequency sweep, and then a wave file measurement technique, which will play any arbitrary wave file that you have saved on your computer. The step sine and chirp measurements allow you to get amplitude and phase information. However, the wave file measurement will only provide amplitude information. The wave file technique is mostly offered for nonlinear systems that do some processing on signals. Typically, noise reducers and stuff, they will try to identify tones and eliminate them, cancel them out. So you'll typically need to play real speech into these sophisticated DSP systems, and that's what the wavefile measurement technique is meant to do. But we'll stick with step sine here. Once you enter the module, you can specify the starting and ending frequencies, how many frequency points you want in between, and then also the number of periods is how many waveforms it plays out before it moves on to the next tone. So the more waveforms or the more periods you play out, the better resolution you'll get, the less noise you'll get in your measurements. And you can have log or linear frequency spacing. I'm gonna stick with linear because log spacing accentuates low frequencies, and that's gonna increase the length of the measurement quite a bit, so I'm not gonna do that. I'm going to select fixed level output, and I'm just going to do 0.1 volts, and I'm going to go ahead and do a measurement. Now we're going to be measuring again a setup that looks like this. So the right channel is a bare microphone. Left channel, I believe, is this tube. Might be switched around. Well, we'll find out shortly. So I'm going to hit perform measurement, and the system will go through the tones and measure it. So this is what the transfer function looks like between those two. The presence of that tube causes all these, causes that ripple in the transfer function response. We can also plot the magnitude of the left and right input channels. And it looks like the right input channel, shown in green, is the one with the most of the peaks. So it's the right channel that has the tube, not the left channel. So if I select dB magnitude here, Aries automatically plots these in SPL. So the signal level at the microphones was between about 65 to 120 dB. So that's a pretty good range. This is typically okay, but Aries does have the ability to specify that you want to keep, you want to produce an output that produces a constant or near constant signal level at one of your inputs. So since the left channel is the bare microphone, I'm going to say I'm going to measurement using a constant L level, constant level at the left input, and it knows it's a microphone, so it asks you for what target you want it to be. I'm going to specify the signal level in SPL, and I'm going to go ahead and specify 90 dB. It should be able to achieve that for the most part. Now, when you do this, it's using a previous transfer function from another data set. Now, we've only taken one data set so far. We've only done one measurement, so we've only got one measurement in our data set list. So we've only got one to choose from. Whenever you hit perform measurement, it takes that data, and if it's successful, it adds it to an array of data sets. You can specify the name of that data set here in a comment. I'm going to specify constant pressure, since we're trying to achieve a 90 dB constant pressure here, and hit perform. So we're going to do this again, and now it's going to adjust the output drive voltage level to try to get a constant signal level at the right channel. And it did pretty good. If I turn the right channel off with all the peaks, you can see it was about 90 dB plus or minus a dB or so. Not bad, but Aries also has the ability to do an iterative technique where you can say use the last transfer function to specify a better output, and it'll iterate a number of times. So if I specify this measurement technique and tell it to do it with two iterations, it's going to do one measurement with just an output of 0.7 volts constant. Then it's going to use that measured transfer function to get a better estimate, and I'll repeat that a total of 3 times, 3 measurements to try to get this as flat as possible. Let me go ahead and do that. This will take a little bit. This is constant pressure, but with iteration. So it was kind of a loud response. Now it's going to adjust everything for the second measurement, and then it's going to do one final iteration. There'll be 2 iterations, and hopefully we'll get a little better than plus or minus 1 dB in here. So now we're, yeah, plus or minus a half a dB. So we did quite a bit better. Maybe another iteration would have done a little bit better. So that's a nice way to adjust your output level to achieve a good controlled measurement level for your system. We'll go back to fixed level. A chirp measurement is a lot like step sine, except now you're specifying how long you want the chirp to be. Here it's 10 seconds altogether. Number of periods is how many waveforms from the chirp will it use to calculate the signal level for one frequency. So it's going to want 50 periods before it says, all right, I captured a frequency. Then it'll go on the next 50 periods and capture the next frequency from that, all while it's sweeping through the level. So I'm going to specify an output, not a 90 dB, but a 0.1 volts, and we'll do a chirp. I'll change the dataset name to chirp and see how this does. So it takes 10 seconds, runs through a linear chirp, and we're not trying to achieve a constant right voltage level here, but we got a frequency response that looks a lot like what we had before. So now that we've taken a number of measurements, you can go to the plotting tab, and all the measurements we took got added to this data set list, and you can have as many data sets as you want. You can get a ridiculous number. But to select one of these for plotting, just click on the data set, a little asterisk will show up, and that's been selected for plotting. So here was our measurement with a fixed level output. These adjusted it for a constant pressure, so I'm going to select that. It might be a little better. Then I'll select the chirp. So you can see that the data sets pretty much line on top of each other, which you'd expect. But you've actually got a lot more frequencies with the chirp measurement than with the step sine. Right click, zoom, and you can look at your data a little closer. If you do have noisy data like that, Aries does allow you to do some averaging in terms of octave bands. If you do a full octave band averaging, your data just kind of disappears, especially on this linear frequency range. So I just turned dB magnitude on and log frequency spacing on. So full octave band averaging there's quite a bit of we've lost a lot of our resolution. But if you go to a 12th octave band, it smooths the data out, and oops, go back to 12. Smooths the data out and looks a little bit nicer, particularly if you need to provide the data in a particular octave bandwidth. This is useful and handy. So that's most of the measurement. I won't go into the wave file measurement. It's kind of specialized, but it's all documented in the manual. If we go over to Files, Clipboard, when you save this to an Aries file, File, Save As, and you save it to an Aries file, I'll hit Cancel here, all of the data in the module is saved to that one Aries file, but you can export this to individual files if you want. I'll select constant pressure, hit save, and a dialog box pops up, and this would allow me to export the data to a .aries _ fr file type. This file can be imported into the modeler module, and it'll keep the calibrated levels intact. So you can do calibrated measurement responses in the frequency response module, and then export that data, and then re-import the data into the modeler module to be able to compare your model results to your measured results. So that's a very, very handy thing to do. Also, you can export the data to the clipboard in text format. Here, if you just click on one of these modules or on one of these data sets and hit copy data to clipboard as text, now I'll open up a notepad here. Let me shrink it down to fit my window. If I hit paste, you'll see a whole bunch of data of the left and right transfer functions. And the magnitude and phase. It's all there. It's kind of complicated. You can also export the data in MATLAB format, which is what I typically do. So I'll select use MATLAB, copy the data out, go back to the notepad, paste, and now I've got text which will create a data structure in MATLAB with all of my complex data ready to go. So that's really handy. And sometimes, oops, sometimes you want all of the data exported. Here you can select copy all of the data to the clipboard as text. If we do that, go back to Notepad, I'm just going to delete that. I will paste the new data in, and you get all of the data. So this is just a massive amount. Typically, you're going to paste this into Excel, not into a Notepad or something. There's also a feature to export the data in XML. So if you select this button, here's all the values that you can export. You can export them as real and imaginary, magnitude, phase, whatever you want. But XML is a little handier. There are some programs that read XML easier than a text file. Also, this tool allows you to resample your frequencies and provide octave band smoothing on that data as well. So if you took one data set with frequency spacing in every 50 hertz, then you took another data set with frequency spacing every 2 hertz, it can be kind of clumsy to put those two data sets together. This export tool allows you to resample your all of your frequencies to match one particular data set so that you have equal frequency spacing on all the data that's been exported. Again, this is detailed in the manual. This has been my introduction to the Aries frequency response measurement module. One feature I did not cover, I'm going to make a separate video for, is this advanced options dialog box, which allows you to do some mathematical manipulations of the data that you took. I call these math buffers. I'll make a separate video on that. Look for that, but I won't cover that here. That's it. I hope this was helpful. It's a very useful tool. Just uses your sound card. You can get some good calibrated data from your systems. Thank you for your time.